So much of the focus of scientists around the world are on type A and type B, but especially type A because of its great ability to mutate. So to understand this better, let me give you an example. So let's say we have two different communities and you are a member of the CDC or DOH, Task Force Flu Monitoring, and you monitor the flu viruses of these two communities. Uh, Take note that these communities, by the way, are far away from each other. Huh? So you will need to ride a helicopter and then a truck and then a habal-habal and then walk somewhere to get to the other community. So on day one on the job, you learned that in Barangay Orange, the virus that causes the flu there is an influenza A virus. But in the other community, Barangay Violet, you find out that what always causes flu there is influenza type B. So you collect isolates and then you take note of the dominant strain. And then you go back to the laboratory and find out how it looks like, the RNA sequences, the antigenic properties, etc. Now, as you continue to do your job, you go back to the community every now and then to collect new isolates. And then you go back to the lab to check or compare how different it is now from the strain you first saw on your first day on the job. All right? So, what you will be monitoring are the genetic changes over a period of time. Okay, so after a few months, you go back to Barangay Violet and then you check the new isolates. And then you observe that it's basically the same as it used to be. It hasn't changed a lot, except for two new point mutations that have happened on two different segments. Okay, so 2-point mutations. So that's a little different from the initial observed strain, right? So you say, aha, there is some genetic change happening here. Okay, and then you go back and check on them again. And you find two more new point mutations. So you go back to your graph and plot that there was a little genetic change that happened again. And then the next time you observe now there was no change. And then the next time there was a little change. And then a little change again and again. No? So at the end of the year, what you will see on your graph is a staggered climb. No? The climb referring to how different the new strain is from the initial strain. All right? And remember, these little changes in the genetic characteristics of the virus were caused by little point mutations in the genes of the influenza type B virus. So this process is actually what we call antigenic drift. Okay, now we go back to Barangay Orange. And like the other community, you also visit them every now and then to check the isolates for changes in their genetic characteristics. So on day one, you plot your findings, and then on your second visit, you find a couple of point mutations also. And on the third, you find 1-point mutation. But on the following visit, an interesting thing happens. You find that one segment is totally gone and is replaced with a new segment, totally different from the first isolate that you saw. So instead of an orange strand, it is now a green strand. So major change. So how do you plot this? So you say, gosh, now 1/8 of the virus is now totally different. So that's a big change from the original, diba? So on the graph, it would look something like this. It's a big jump from the original form, a big genetic change. And then you go back, and then you find that the green segment now has a point mutation. So you plot that minor change. And then you go back again because you're very loyal to your job. And then you find that another segment has totally changed. So you have another very big jump. And then at the end of the year, you look at how different the new strains are from how the strain originally looked like. So you see, the genetic change of the viruses from Barangay Orange is quite different from that of Barangay Violet, right? So this pattern actually shows some antigenic drifts also, no, from the minor point mutations in the virus. So again, these point mutations result in minor changes in the amino acid sequence of the proteins of the virus, no, altering the antigenic sites on the surface proteins, allowing the virus to escape recognition by the immune system of the host. But this big, major change in the genetic sequence is what we call antigenic shift. Okay, so this reflects drastic changes made in the sequence of viral surface protein. And you will find another genetic shift here, antigenic shift here at the end of the year. Okay, but let's look more closely on how this antigenic shift actually happens. So let's say we have a virus here. You have the envelope. No? Then you have the 8 blue segments that code for the specific proteins, right? So now the hemagglutinin that one of the strands codes for produces a violet H. So I'm drawing them like a hand because remember, diba, they grab onto the sialic acid receptors. So, and then the 5 fingers are the 5 antigenic sites, just so you will remember them better. And the Na coding strand produces a yellow neuraminidase. So, scissors, no? Because, diba, they cut sialic acid. Okay, so yellow and purple. So, after a period of time, you check again and find that one of the segments has a point mutation, causing one of the antigenic sites of the H protein to become blue instead of violet. So this is only a minor change. So this is what you call the antigenic drift. And this can happen actually in all types of influenza viruses, not just the type A. Okay? So now, because these are only minor antigenic changes, immunization with this strain of influenza can still give protection to the host even if there are minor changes, because the antibodies formed against this specific virus will still be able to recognize the virus, no? Because the changes are minimal. But although these changes are minor only, they can mount up over time and produce a slightly different phase of the same surface protein. So this allows the virus to be able to escape recognition by the immune system and possibly result in the illness on the host despite immunization, right? So this is one reason why there has to be a different flu vaccine every year, okay, to account for these changes. Actually, if the host does develop illness, it is usually just mild because to a certain point they already have antibodies to that strain. But now let's say a pig gets infected with 2 different influenza A viruses. Kay kung maingon magud kog tao, murag swerte kayo, no? Okay, so one virus has the blue segments that code for the yellow H and violet N proteins. Okay, so let's say that the violet H's are H type 1 and the yellow N's are N type 1. So we have an H1N1 virus. So this virus is also known to be able to also infect humans, di ba? Aside from pigs. The other virus is also another type A virus, but this time with green segments. So green segments, red H's, and white N's. And the red H's are H type 5 and the white N's are N type 2. So you have H5N2. But let's say this virus is only able to affect the pigs and birds only. So example lang ha. Okay. So both of them infect the host cell. They take over the cell and replicate themselves, producing more blue segments and more green segments in the same cell. Okay? And remember, the endpoint of producing these segments is production of the proteins assigned to them. No? So the blue segments produce violet H's and yellow N's, right? And the green segments produce red H's and white N's. Okay? So when it's time for them to bud, they assemble the viral components. So one virion receives all blue segments, and thus it has the yellow and violet proteins, similar to the original virus, right? So the name would still be H1N1. Another virion unit receives all green segments, so the same. It will have the red and white proteins. And again, like the original, it is H5N2. But interestingly, once in a while, mixing between the viruses can occur. One virion can receive 6 blue segments and 2 green ones, producing, let's say, violet H's, but this time white N's. Now, this is a totally different virus than any of the viruses that infected the host initially, right? Because basing on our color scheme, it is now H1 because of the violet H and N2 for the white N's. So H1 and 2. And the other, it got 5 green segments and 3 blue ones, producing, for example, red H's but yellow N's. So this is now H5N1. Okay? So totally different new viruses than the previous. This is actually what happens in an antigenic shift. Okay? And now, when originally H5 flu viruses were only supposed to infect birds and pigs, because of the N1, they are now able to infect humans also. Okay? So another new virus infectious to humans. And this is what causes epidemics. Actually, in the last 100 years, there have been 4 epidemics due to this, no? The antigenic shift. So why an epidemic? This is because the antibodies made against the previous strains will not be able to recognize the new strains anymore. And while we're at it, these antigenic shifts occur in non-immunized people, but affects even the immunized ones now, after. No? Because the virus is actually a new virus na, never been heard of before. And remember, this also happens in birds and other mammals, no? Bats, pigs, horses, etc. So this is also why it is equally important that poultry owners immunize their products, or sa bang term, dili man pets, di ba? And take note, you don't have to eat them to get infected. Okay? And if this epidemic is not contained within the region, and then it spreads to multiple countries and continents, it becomes a pandemic.